that there's really a limited way in which you can structure it, your hypothesis test. So for a linear regression t-test, we're always assuming it's a two-tailed situation. It conceivably could be one-tailed, but the problems that we'll be focusing on and that are the focus of the AP are two-tailed. This is page 42. All right. So the assumptions behind the linear regression t-test, it's got to be linear. So the relationship, I mean, they say it has to be linear. Well, if it is linear, then why are we testing it? So there's an assumption that there might be an underlying linear relationship, and that's what we're trying to test. Right? Independent observations, a normal distribution, equal variance. Almost always that's something that you have to assume. Right? So that one, standard deviation of y is the same for all values of x. Right? So without having the population data set, I don't know how you would verify that, so you just assume it. And random. Right? All of our studies, everything that we've done with hypothesis testing, have all involved random samples. So that's something that you can assume. When you're given a problem on the AP, that piece of information has to be given to you, unless you're generating the data yourself, which I've never seen on the exam. Right? I've never seen a situation where you randomly generate a data set and then perform a hypothesis test on it. Right? It's just too open-ended. It would be a nightmare to grade, so they just stay away from that. All right? And they're certainly not going to ask you to collect data during an exam. It's like, okay, look around the room that you're in and identify the number of people who are wearing hooded sweatshirts, and that'll be the number of successes and number of trials will be the people in the room. It's just not going to happen. Right? So they have to give you a random set of data. You may have to, and I'm going to amend that and say you will have to verify that it's a normal distribution if they give you a raw data set. If they just give you summary statistics, then it's just a matter of reading the question and making sure that it says approximately normal distribution. Right? Sometimes they don't say that, but they ask you to perform a hypothesis test anyway. If that's the case, then you would have to assume a normal relationship. All right? So yeah, I'll take you through an example. 5 small cities in California gave information about a percentage of 16 and 19-year-olds not in school and the death rate per 1,000 residents. Right? So, how would those two variables be related? I mean, if you think about all the different underlying variables that go into it. You're not in school, you're 16 to 19 years old. Right? Probably means that you dropped out of high school. Right? So if you drop out of high school, you're depending on what you do after dropping out of high school. I mean, maybe you go to trade school, in which case you become a plumber. Again, going back to that, if I had to do it all over again, plumber came to the house, fixed the drain, been leaking for about a year. It's the only time I could get him in. 20 minutes worth of work, $475 check. And the part, I believe, only costs like $80. And that's what he told me the part cost. I mean, I trust the guy. Seemed like a decent dude. I'll use him again. But yeah, for about a half an hour's worth of work to get around $400. I went down the wrong career pathway is what I'm saying here. All right, so recalibrate everybody. No, I'm just kidding. You want to go strike it rich. And if you're going to do that, you got to go to business school. Right? Finance, that's the ticket. If you want to be like absurdly wealthy, that's the route you take. And if you want to just be like everyday wealthy, plumber. Right? I'm fine with everyday wealthy. Anyway, so the individuals in this case possibly did not become plumbers. Maybe they got no further education, didn't have a whole ton of money, and because of that made poor health decisions, and because of that it impacted the death rate. I mean, that's a possibility, right? That's what we're looking to study here or to determine, right? Can the percentage of 16 to 19-year-olds not in school be used to predict the death rate, right? So 2 ways to handle it. One would be to do a confidence interval. The other would be to do a hypothesis test. And we'll do the hypothesis test first. So what happens is when you're dealing with a sample, the linear regression y hat is equal to a plus bx. All right, this is for the sample. I'll move that over actually a little bit. For the population, right, because again, just because we collected a sample and it shows a relationship, you know, thinking back to Unit 4, it showed a relationship and you say, okay, there's strong positive linear correlation between the two variables. That doesn't mean it necessarily projects out to the population. This is a random sample. We want to know how it interacts with the population, right? The population regression equation is capital alpha, which looks an awful lot like a capital A, plus capital beta, poor quality, beta, and you know, X, independent variable. So technically, these should actually be alphas and betas of the lowercase variety. I think my app's about to crash. It just froze on me. Okay. But my undo isn't working, so I don't know. I'll just have to deal with that. Use my lasso tool. Get rid of that. Right? So, yeah, technically those are supposed to be lowercase alpha, lowercase beta. We just use A and B for convenience. Right? And also not to confuse it with the alpha value in a hypothesis test. I mean, we overuse variables all the time, or in constants and coefficients. Right? So the null and alternative hypotheses are always beta equals 0, beta not equal to 0. Right? Which creates a two-tailed test. Right? The degrees of freedom is equal to n minus 2. Right? It's minus 2 because we have two variables. We're subtracting a degree of freedom from each one. Right? Essentially. We have 5 sets of data. So 5 minus 2 is going to be equal to 3. So that's my degrees of freedom. That gives me the critical value, or helps me get the critical values for t. All right, so probability distributions, students t, inverse, alpha value not given, we'll assume a 0.05. All right, so that's split evenly among the two ends. So 0.025, 0.025, and then a 3 for the degrees of freedom. So I have negative 3.182, positive 3.182. So same structures. Frozen screen.
Why is the degrees of freedom -2 now, not -1?
Because we have two lists of data. So two variables, we subtract one for each one. Good question. So the test statistic is going to be t equals b minus beta over s sub b. All right, we'll define the s sub b in a minute. But we could get a lot, almost all this stuff from the calculator, so there's really no need to kind of reinvent the wheel. On the formula sheet, I'm going to give you a copy of the formula packet, I should say, in a little bit. But all that information is on here. Right? So at the bottom of the back side of the first page, it tells you what the point estimate is, the population parameter, beta, and then the standard error. They define S sub b as S over the standard deviation of the x variable divided by n minus 1. But then they define S to represent something even more convoluted, right? So for our purposes, we can just go to the calculator, kind of like the chi-square, and get what we need from there, all right? So we'll get the p-value. That's going to be because it's two-tailed, probability that t is less than whatever we get as our computation for the test statistic. All right, so let's get this stuff in the calculator. Small set of data, so it's not going to be overly difficult. All right, we go right to the inference menu. Under test, you'll see one that says slope. All right, so use the slope test. Now, all this funky notation aside, essentially that's what we're doing. The b value in the a plus bx represents the slope. We want to see if the sample slope is a good estimate or estimator for the population slope. All right, so that's why we have a lot of b's here. And the S sub b is the standard error of the slope. Now, if you're given one of those computer printouts, all that information is there. You just got to pluck it from the print. I'll show you that in a little bit. I think I might have put one on in the packet that I gave yesterday. So I gave the raw data and the printout table, pretty sure. So you'll see the relationship there. But for now, into the calculator, null and alternative. They give you the option for greater than, less than. If they say, if a question is posed as test the claim that the population slope is positive or negative, that's when you would use the alternatives of greater than, less than. But if they're saying if one is or asking if one could be used to predict the other, they're just looking to see if there's a significant linear relationship. Doesn't matter which way. All right, so I'm changing this to not equals. Next, then you got to type the data in. So kind of like the chi-square, the data entry is slotted into the app itself. The good news is when you type the information in here, it also goes into the regression app. All right, so the x1 that I type in here is the same as the x1 in the regression app. And if you needed to find means, standard deviations, make a graph, things like that, you would go there for it. All right, so it's not a double dip. You don't have to type it in a second time. Or maybe that is what a double dip is. I don't know. My idiom game is a little out of whack. All right, I decided on a 0.05, so I leave that as is. It gives the test statistic, it gives the p-value and the degrees of freedom, so I'll just slot that stuff in there. So negative 2.144, and my p-value notation-wise, negative 2.144 goes in there and gives a result of 0.121. All right, so I'll get into the framework of the test statistic in a second, but as far as drawing a conclusion is concerned, we have everything we need. The p-value is not less than the alpha value, so I'm not going to reject the null. I'm going to keep the null, and what that says is that there's no significant linear relationship between the two variables. All right, so you might be wondering how we know that there's no relationship if we just did a study on the slope. It goes back to, this is also a formula that's given to you. It's on the first page. It's, I'll just write it. I'll write recall, classic textbook lingo. All right, the R value is equal, well, you can go either way with it. I'll put the formula that they have here first, and I'll show you how it's actually helpful for us. All right, so B is equal to R times SY over SN. All right, the slope, you would get that by taking whatever your correlation coefficient is and multiplying it by SY over SN. All right, but if I modify this, right, this they don't give you, but it's easy enough to do. You can solve for R I'm just trying to do an arrow here. If I solve it for R, oh, Sn, jeez, Sx. Right, so if I solve for R, it's equal to B times Sx over Sy. All right, Sx and I can't even talk anymore. That's why it has to be the last lesson of the course. I have no words left in me. This is always positive. Right? If you think about finding a standard deviation, you find the differences between each x value and the sample mean, you square it, you divide, you take the square root, it's always going to generate a positive value. So Sy, Sx, or proportionally Sy over Sx, or vice versa, always going to be a positive relationship. So that basically makes it irrelevant in terms of determining the relationship between the slope or the type of relationship between the slope and the correlation coefficient. All right, so if B is positive, R is positive. If B is negative, R is negative. If B is 0, R is 0. All right, so drawing a conclusion about the slope helps us draw a conclusion about the correlation. All right, so if the B is positive, then R is going to have a positive linear relationship, or show a positive linear relationship. If B is negative, R is going to show a positive linear relationship, but in the negative direction. Not a positive, a linear relationship, but in the negative direction. And if it's 0, if the slope is equal to 0, the line is horizontal. Right? If the line is horizontal, there's no relationship between the two variables, because no matter what the x variable is, y is always the same thing. All right? Now, what this test does is it establishes significance to it. All right? So if I got a p-value less than alpha, I would be saying that there is a statistically significant relationship in that the b value, the beta value I should say, is not going to be 0. Right? So statistical significance means that in this case, if it's not equal to 0, there is a linear relationship between the two variables. Just a question of whether it's positive or negative. Right? And so by knowing that about the slope and this relationship here, we know it about the correlation coefficient as well. All right. So I could draw my conclusion, but I'm going to hit next here. Get a look at the picture. I kind of like it in the sense, I mean, I can't zoom in, but that little shaded area, the diagonal shading, that gives me the location of alpha, and the orange is not, it's beyond the alpha shading. So that's a nice way of establishing that you're not rejecting the null. Also, like I said before, I can go into my regression app. Data's already there. Go to stats, and I have lots of things here. All right, the X1 list ends after sample standard deviation, because that X1 list, I mean, you can't find things like the sum of the products if you're only looking at a single list. All right, so when you go over into the Y1 list, you see you have the standard deviations, the means, and things like that. Actually, they don't give the mean. Right? Well, they give you the standard deviations for each of the variables individually, and then if you go down the line, you get your correlation coefficient. You can see it's kind of verified, right? In the sense, well, is it verified? I would say that's moderate, borderline strong linear relationship. So it's not enough to say that we could settle on it being like a strong negative linear correlation, right? But it's borderline. And so the 0.121, that's also kind of borderline. If I chose an alpha value of 0.10, it's in the neighborhood. So it's kind of flirting with the idea of having a strong relationship. All right. Let's see, anything else from here? I mean, if they wanted you to state the correlation coefficient, you can get it from here too. You could also create the graph, do the regression. You remember that from the last unit. Linear, select the one that's a plus bx. You get all that stuff. You can get your equation if you want it. You know, all that stuff is there. If you need a residual plot, you know, if this question's one of those combo platters, like number 6 in the free response, the one that takes half an hour, like they may ask you to do all this stuff. So it's good to know where you could find all that information. All right, and then you can make predictions and stuff like that. All right, so I'll write the conclusion in a little bit, but I wanted to take you through the confidence interval also. We'll do 95% confidence. All right, and so the formula for that is B plus or minus T alpha over 2 times S sub B. All right, the standard deviation or standard error about the slope. If you're given just a raw list of data, you just do it the way I'm doing it here. If you're given a table, you know, one of those computer printouts, then you want to pull the appropriate information from that. So in this case, I'm looking at, I already lost it. Where's my, oh, I never actually wrote the B. That's why. All right, so my B is negative 0.109 approximately. So negative 0.109 plus or minus T of, well, alpha is 0.05. Alpha over 2 would be 0.025. 0.025 times S sub B. Now again, the S sub B formula, I might as well walk you through that real quick. I'm going to steal room from the bottom here. I didn't space this out very well. All right, so S sub B is equal to, it's not pretty, S over S sub x times n minus, well, square root of n minus 1. Radical. I'll just leave it like that for now. And then they tell you that S itself is the square root of the sum of y minus y hat squared over n minus 2. Figured I would talk to you about it because they put it on the formula sheet. If they put it on the formula sheet, there is an expectation that you're probably going to have to use it at some point. All right. The unfortunate aspect of that, just like any other exam, is the time that a student may use these formulas may not be this year. You know, it could be on the exam, so we prepare for it, but then you come back the next day and you're like, yeah, that nasty formula wasn't, they didn't ask us anything about that. And that could be one of two things. Either you didn't know enough to know that you needed to use the formula, or they just didn't ask. Either way, it's kind of a negative feeling, right? So the y minus y hat part of it is the set of residuals. All right, so what you would have to do, I'll just kind of talk you through it, is you'd have to find the residual for each value, populate a list with it, square all those values, add them up, divide by 2 less than the total number of values in the set, then take the square root. All of that would give you this number here. All right. Sx, we actually already had that. That's the standard deviation for the x variable. All right, so if I go back to my stats, the sample standard deviation for the x variable was 4.92 and change. All right, so you have that information. The only thing, unfortunately, that they don't give you, and I think it's, I'm just making sure, sometimes after you do the regression, it shows, some more information shows up. They don't give you the standard deviation for the set. They just give you the standard deviation for each individual variable. So this, if you were given a raw list of data, they may ask you to compute this, right? So you just got to be prepared for it. But in terms of actually carrying out the confidence interval, confidence intervals, slope, 95%, all right? So they give you the standard error here. Again, if you have to show the work, you got to use these formulas. But that SE, that is the S sub B. All right. So the SE, it's weird. You got to kind of hunt around through the different apps, different menus, but eventually you can find the numbers that you're looking for. The SE is the standard error. And it's the standard error for the slope because we're testing a claim about a slope, right? So they actually have that, but you got to look around for it. All right. They also give you the margin of error, which is going to be the result of this computation here. Cross that bridge in a minute. But I'm going to write t of 0.025 times 0.0508. Then I'm going to do negative 0.109 plus or minus 0.162. Degrees of freedom already accounted for. One really good aspect of the inference app is, let's say you forget. I mean, the question before is why is degrees of freedom n-2 now instead of n-1? Maybe you forget that on the exam, but the app's not going to forget. So you're like, oh, why is degrees of freedom 3 here and not 4? Like, oh, this is the one where you subtract 2. So you can kind of pull it out that way. And then you get your confidence interval, negative 0.271 to 0.0528. Yep. All right. Now, if 0 is in the interval, that means that 0 is just as plausible as any other number in the interval. If that's the case, then we cannot reject the null hypothesis. That's what I was saying before. I mean, it kind of got lost in the shuffle as we got, we dug deep into the hypothesis test. Kind of got lost in the shuffle that unless they ask you specifically to perform a hypothesis test, you can do a confidence interval. All right? You still have to identify your null and alternative hypotheses, but you can skip all of this stuff here and apply an appropriate confidence interval to draw the same conclusion. Right? So that part is up to you, and they give you that flexibility on the exam for free response. You can, in every exam I've ever seen, you could do a confidence interval to answer their inference question. Right? It's only in the multiple choice where they're going to ask you things like test statistics, p-values, and stuff like that. And you're like, oh, okay, so I still have to know some stuff about hypothesis tests. And I'll tell you, even on the group test on Friday, if you wanted to do everything with a confidence interval, you could. I set it up that way, right? I'm not going to say at the 5% level test the claim. I'm going to say what was the question here? Can the percentage of 16 to 19-year-olds not in school be used to predict the death rate? At no point did I say hypothesis test or confidence interval. I didn't even give an alpha value, right? So you can answer all the questions without even touching a hypothesis test, but done enough with it so far that you may want to. I don't know. Right? So in this case, I would say there is insufficient evidence to reject the claim that the slope between those two variables, I would state the variables, is 0 at the 0.05 significance level, and then I would answer the question that was posed. All right. So there is insufficient evidence to reject the claim that the population slope always got to say what the slope is relating to. You could say slope between or the slope relating to. Regardless, it has to be, what is slope? Change in y over change in x. So the population slope between y variable and x variable is.
Yeah. So like when you did the test statistic part of it, like on first half, could you say there's sufficient evidence? Like does it?
There would not be sufficient evidence because this number does not fall in the shaded region. Falls short of it. Between death rate and age, I'm going to say. Oh, no, it's not age. Percent. Yeah, I got to actually phrase that. I don't want to say dropout. So death rate and percent not in school is 0 at the 0.05 significance level. Got to make a statement connecting our analysis of the slope to the correlation, because they said, can the percentage be used to predict the death rate, right? Since correlation, no, I don't need a comma there. Since correlation is directly proportional to slope, there is no significant correlation between the variables. Is boy. I've already stated what the variables are, so that's covered. All right, so that's the bridge to allow the discussion of predictions to happen. So we would say we cannot use percent not in school to predict the death rate. Writer's cramp. All right. You're going to find yourself, when it comes to these inference tests on the AP, it's going to be like an essay along with the computations. Like, you got to explain every single thing you do. Right? Defining variables. Don't assume that people know what your abbreviations mean. Define your abbreviation. I'll show you some sample responses for the inference test part of it. I mean, when they ask you to make a graph, making a graph is easy. You know how to do that. But then the narrative part of it, like you have to do a write-up addressing center shape spread and outliers for any graph that you produce. So in a case like this on the AP, and again, I'll get into all the detail that needs to be accounted for. We have to address whether each of the two variables can be from a normal distribution. Right? So what we do is we graph each of those variables, create a box plot, a bar graph, not bar graph, a histogram. And then for each of those graphs, you have to address center shape spread and outliers. So that's why that number 6 is the beefy problem. If it is an inference test, you're going to take every bit of those 30 minutes. Right? If you find yourself being like, all right, no alternative, graph, test statistic, p-value, small conclusion, done. Hey, that wasn't so bad. You probably didn't do so well on that. All right. So I'll give you the precise breakdown, and I'll show you some sample responses. After we get through this unit test. All right. So one app to another within the numworks. All right. So unfortunately, it's not all self-contained in one app. You got to get information from each part. All right. So we're testing a claim about a slope. Remember, so recall, y hat is equal to a plus bx. That's for a sample, any sample. All right. Now, this is something that we haven't talked about, but if you want the population regression equation, it's capital alpha, which is basically capital A, plus beta, capital beta x. And so that's for the population. So we're looking to see how the sample relates to the population. But in order to do that, I need to know this equation, right? But before we get into that, let's just set up the structure of the hypothesis test. You have HO, HA, beta as a default will be equal to 0. Oh, I'm going to turn that off. Beta as a default is going to be equal to 0. And when beta is equal to 0, that means the slope, population slope, is equal to 0. If you remember, the only instance in which there is no correlation between two variables whatsoever is when the slope is equal to 0, because that produces a horizontal line. And in a horizontal line, it doesn't matter what the x value is, the y value is always going to be the same. So they're completely unrelated to one another. Right? The alternative to that depends on what the question's asking. If it says that there's a significant association or there's a relationship or correlation between two variables, then the opposite of that would be that there's no significant, right? So that would be an equal versus not equal instance, right? But they could also say, test the claim that the slope is positive, greater than 0, negative, less than 0, right? They could also say, as an extension of this, test the claim that the correlation is positive, negative, or whatever. All right? We're just talking about slope here, but in your AP formula sheet, you have a rule. They give it to you, and that rule states that, and it's on the first page, it's B equals R times SY over SX. All right, that creates a proportional relationship between B and R. I could even solve this for R and get B times SX over SY. All right, standard deviations always have to be positive values, right? Just through the operations used in performing a computation related to standard deviation. We find differences, but then we square them to make them positive. We divide, take the square root, still remains positive, right? So these values are always positive. So they actually have no bearing on the sign of the correlation coefficient, or if you have the correlation coefficient, the slope, right? So what that tells me is if R, I'll use the second one because that's the one we're really addressing. If B is positive, then R is positive. If B is negative, R is negative. If B is equal to 0, then R is equal to 0. Right? That's the beauty of a proportional relationship. So, going back to my null and alternative hypotheses, if I establish that my population slope is equal to 0, then I've established that the correlation is equal to 0. And on the other hand, if I establish that the population slope is not equal to 0 and there is significance, then I can conclude that there is a significant linear correlation between the two variables. All right? And all of that is going to have to work its way into your explanation, so I'll show you how to do that in a little bit. But in this instance, it is a linear regression t-test, so I'm going to draw a t-distribution, two-tailed because it's a not equal to symbol. They did not tell me what the alpha value is, so I'm going to assume alpha, so I'll let alpha equal 0.05. So 0.025 on either side. Right, I need my critical values. But in order to find the critical value or values for a t-distribution, you need to know your degrees of freedom. So in this case, for linear regression t-test, degrees of freedom is equal to n minus 2.
Oh.
All right. Two variables, subtract one twice. All right, so yeah, messes everything up. Everything we thought we knew is wrong. All that good stuff. So my population and eating versus drinking, or eating or drinking, I guess. I don't know.
What is it even measured? Like, what is the percentages for population for?
So the following comes from a study of small cities in Illinois and the habits of their residents with regard to eating and drinking. Note, it's more expensive to eat out than at home. So the population is whatever it is in whatever units it is. I have no idea, maybe thousands.
Oh.
Eating and drinking, they're talking about expensive, so I'm going to assume they're talking about money. So now it doesn't have a whole heck of a lot of context. So we're talking about money per day, money per week, like who knows, right? So any problem that you get for the assessment and also the AP exam is going to be way more detailed, right? But here we're just looking at our two variables. First one's X, the second one's Y. Let me go to my calculator. Degrees of freedom, and so 1, 2, 3, 4, 5, 6 minus 2. Right, the n represents the number of pairs, ordered pairs, so 4 degrees of freedom. Now, if you get jammed up and you forget the rules for degrees of freedom, in the inference app, it computes that for you, right? So you'll look at it and say, wait, why is it 4 instead of 5? And you'll be like, oh, this is the one where you subtract 2. Guys, we listening, or are we doing the pony ride? A little bit of both. Bit of both. All right, so distributions, probability distribution, students T, inverse 0.025 with 4 degrees of freedom. We got negative 2.776 and also symmetry, so 2.776. All right. Now our test statistic. This question is asking if there's a significant association. Did not say that we have to do a hypothesis test. We could do a confidence interval, and you'll have that freedom when you take the assessment. As long as you're proving what needs to be proved, then you have license to use a hypothesis test or a confidence interval. I'm not going to stipulate that you do it one way or another, right? But in this instance, what I've discovered with NumWorks is that if you do the confidence interval first, then it gives you the ingredients for the associated hypothesis test. Normally do hypothesis test first and then follow it up with a confidence interval. Here, I'm going to start going down the path of doing the hypothesis test, and I'm going to bounce to the confidence interval and then come back, right? Test statistic formula. In its most simple form, T is equal to B minus beta over the standard error of the slope. All right. The B we don't know yet because we didn't run the linear regression, which we'll have to do. The beta is going to be 0. That comes from the null, so that's fine. And we have no idea what the S sub B is. So we could go to the inference app, but I'll tell you, for whatever reason, it doesn't give you the standard error of B in there. So we're going to bounce over to the confidence interval.
This is another one you can't use inference for?
It's another one where the inference app doesn't give you everything you need, but if we bounce between a few different apps, it'll actually do the job for you. So it's weird. Just watch, you'll see. So confidence of 95%. So alpha is 0.05, alpha over 2, 0.025. The rule, B plus or minus T alpha over 2 times S sub B, right? Because it's always multiplied by the standard error, right? So the standard error we're just representing with an S sub B, right? So I need my regression equation. So let me get my data in. I'm going to go to the regression app, type in this stuff. Bless.
Thank you.
All right, so you get your data in, and just like we did back in Unit 4, go to graph.
Verify.
You get a look at the picture. I'm not seeing anything really linear about this, so I kind of feel like the conclusion is writing itself. But go to regression, a plus bx, and then back to regression, which is my least favorite part of this app. And it gives you the formula or the equation for the regression line, which I'm gonna just jot down up here. Y hat, is equal to negative 36.318 plus 1.438. I'm gonna just check for scientific notation here. Up, hit something weird. All right, so just an X at the end. All right, so this is the B value. All right, so we need that information. We actually needed to run the regression. We get an R value, which makes me think that this is probably going to be a good fit for the population, but we'll see. All right. I could go into stats and see if there's any information, useful information in there, but like I said, this is one of the weird ones where you got to kind of bounce back and forth. Right, they'll give you the sample standard deviations for each individual variable, but it doesn't give you the standard error for the slope, and it doesn't give you anything related to the population, so we have to pull that out. But we do have the B value, so that's great. So we can put the 1.438 plus or minus. I need my T alpha over 2. All right, so that was 2.776. I just need my S of B. All right, so for that, into inference, intervals, find the one that says slope. All right, so it's inference, intervals, then slope, hit OK. It hangs on, which is really nice. One thing that's finally kind of nice about this process, it hangs on to the data that you typed in the regression app. It also goes the other way. If you type the data in here, it'll put it in the regression app. All right, so that's kind of nice. Significance level, 0.95, next. Now you have your critical value. That SE is what we're looking for.
Yep.
SE for standard error. Standard error for the slope, because we're in inference for slope. So now I have the value that I was looking for, about 0.372. I got the margin of error, which is them very nicely simplifying this for me, 1.0325, 1.438 plus or minus that. And then the actual interval, 0.406, all the way up to 2.471. All right. Now, it's kind of absurd that the upper bound is anything greater than 1. That's the highest value that you could have when dealing with correlation. But this is talking about slope, right? So what we would have to do in order to figure out what this is in equivalent correlation form is we'd have to use this formula, right? So we could find the confidence interval for correlation, but then what we would have to do is find R is equal to B times SX over SY. All right. Now this question's not really directly asking for that, but it's sort of implied. Is there a significant association, relationship, correlation, right? So I have the B value, right, or at least the estimate of the B value. So I'm going to put in the 0.406 for B, because that's my low bound for my correlation. I'm sorry, for my slope. I'm looking for the corresponding R value. So I'm going to do 0.406 times, I got to go back, bless you, to the regression app, grab my SY over SX. So that's the standard deviation for the X variable, 16.228. Divided by 26.274. Bless you, bless you. All right. So this is going to give me my low bound. These are, again, this is a confidence interval for slope. All right, so I'm going to get my low bound for R, and then I'm going to do it again, this time with a 2.471. And through this process, I'll get my confidence interval. All right. So
how'd you get a 2 point? Wait, oh, so you're just doing both of them?
yeah. So I'm taking the low bound and the upper bound. All right. So I got to run these numbers. So now back to the calculation menu. All right. So 0.406 times 16.228 over 26.274. So I'm getting 0.251. And then on the upper bound, so we still get an upper bound that's bigger than 1, but when we're talking about correlation, it could never be bigger than 1. Right? So you could actually cap it off at 1. But what this is saying is that with 95% confidence, we could expect the correlation coefficient to be between 0.251 and 1.526. So we are 95% confident that the population correlation between whatever it was, population and eating, drinking. So overusing the word population, but that's what they're talking about. Is between 0.251 and 1.526. All right. So we took care of the confidence interval, but then now we got to go back and take care of the associated hypothesis test.
Wow.
Just keep that zoomed in. Fortunately, we have all the numbers. It's just a matter of putting it all together. All right. So the B value, 1.438, lowercase b. The beta, capital beta, 0. S sub B was 0.372. All right, so we get that number, 1.438 divided by 0.372 is about 3.866. All right, that falls in the shaded, or one of the shaded regions. So that's telling me that I'm going to reject the null. So the p-value, because it's two-tailed, 2 times the probability that t is less than or greater than this number, it doesn't matter. But if it's less than, it's got to be negative, because we're looking for the fringe values. Now, for this, well, one, to verify what we just did, but also to have it do some of the computations for us at least, we go back into the inference app, this time test, slope, we want a not equal symbol, data's still there, 0.05 is my alpha, See, it only gives us the t and the p value, but that happens to be what I need anyway. So I'm going to change this 6 because I did some rounding along the way. I'll make it what the calculator says.
Wait, where did you give me the p value?
Right below test statistic.
For slope?
Yeah. All right, so my p-value is less than the alpha value that I chose, so I'm going to reject the null hypothesis and go with the alternative. Now this is related to the confidence interval for slope, so this one here. You'll notice that there is no way that 0 could be in this interval. Right, the interval is entirely in the positive neck of the woods. Right, so that would be how we could draw the conclusion for the hypothesis test. If that population parameter, the assumed population parameter is not in the interval, then we reject the null hypothesis. Right? So doing this work here can help you avoid having to do this work here. Right? And especially in this case where you have to do this work here to do this work here, it's kind of a double whammy there. Right? So there is, let me zoom in here so I can write, sufficient evidence to reject the claim that the population, now this time it's going to be population slope, but you have to state what the slope is relating. So slope for or between eating, drinking, y variable first, and population is 0.
Or you do y first?
Yeah, like you think of slope, change of y over change in x. We always talk about the y variable first in terms of changes in the x variable. At the 0.05 significance level. Now the issue that we run into is that this does not give us enough, assuming that you didn't do the confidence interval, this doesn't give us enough to answer the question. We have to tie slope to correlation. So since slope and correlation are directly proportional, we can say that the correlation coefficient between the variables, because now we know what they are, or we've stated what they are, is not 0. All right. If it's not 0, that means there must be a significant relationship. All right. We can say or support the claim that there's a significant association between the variables. Yeah, I don't know if he's going to help you on this. Never hurts to ask, though.
Wait, so is this one of the questions that could be on the test somewhere?
What a way to end the course.
Should never edit letters to
Oh, yeah. And, yeah, if they ask you to do a free response question related to correlation, you can damn well bet it's going to be number 6.
It's only one FRQ.
And this would be kind of an incomplete answer because I didn't address the normality. Like we need both x and y to come from populations that are approximately normally distributed. So I'd have to make a box plot for each variable x and y,
Oh, wow.
put it on paper, address the center, shape, spread, and outliers. And also, just going back, if there is an outlier, then the measure of center has to be the median. I can't use mean and standard deviation if there's an outlier present in the data set. Right? I'd have to use median and interquartile range. So a lot of ingredients. When we start hardcore reviewing for the exam, I'll show you some sample submissions. And then you'll look at it and you'll say, oh yeah, that looks like what I would do. What did that student get? Oh, a 2. Okay, that's probably not good. So then I'll show you what a 5 looks like. And so you can start working towards thinking along those
Wait,
lines.
this it's graded on 5 points.
AP.
Yeah, it's APs out of 5.
Did you get 100 on the vacation?
Oh wait, no. You mean the score?
If he said he got a 100 on the exam, I think he might be not telling the truth.
No, I mean on this. You mean five? You mean they got a 5 on the exam?
Yeah, so 5. The
Yeah,
free
how's, like,
response
the
questions are
FRQ?
graded on a scale of 1 to 5.
Oh.
Yeah.